Good afternoon, ladies and gentlemen. Well, it's afternoon here. East Coast, United States, Florida, Northeast Florida. Anyways, today's subject is going to be billets. Okay. Nowadays, in this technology that we have, this level of technology that we have now today, most of the billets they make are put through machines. I mean, in other words, they're generated by machines. The furnaces will melt down the metal, the proper alloys and additives. They pour it into a big machine that extrudes the either it be square or round, long pieces of metal that are extruded like I don't know if you had one of these when you had Play-Doh. You had a little machine that you opened up. You put a chunk of dough into it. You close the machine and you squeeze the handles, and maybe a long star might come out. Maybe a long bunch of spaghetti strings came out, and maybe a long square piece of material came out. Depended on what you put in front of what kind of doggone it, the piece of plastic that you would put in front of the opening of the little thing you would squeeze would depend on what shape the material would come out. Well, nowadays we have that type of a machine too. Essentially, it just squeezes out like toothpaste out of a toothpaste tube, the metal as it's solidified, and they chop it with a big machine and they send it down a long roller, and the roller will put it through more heat and get it all heated up so that it could get formed in between big rollers. And that kind of setup, that's not what I'm going to be speaking of today. I'm going to speak of the old school way of doing billets. And it's but for those of you who've never seen that manufacturing process before, in the description I'm going to attempt to put a address or a connection or whatever you call it in the description for a film that was put out by a company that does all that, and it was a well-made film. So I thought you might enjoy to see that too, to get an idea of how your billets are made today. Now, a billet, what's a billet? Basically, it's a chunk of metal that's been formed. Mostly, it'll be in a cylinder shape or into a long square shape. Okay, there's limits at which the piece of metal the limits in size, as which the piece of metal will be before it goes from billet to a slab, or a billet to something else. So I highly advise you to go and watch that film either before or after this one. Or not film, but video. Before or after this one. Maybe after this one, just to see how much easier it'll be on the people who have multi-million-dollar machines. Okay, I already tried to do all this, explain all about billets before. And this, what you see right here, was the very end of all that. And it turned out, well, I made a dang stupid mistake again of wearing this camera on my head. Because you can't tell, you just don't know what is and what is not being captured by the camera when it's on your head. And I had about an hour worth of jabbering at you, and then I went and scoped it out, and practically half the stuff down here, all of this was invisible. You couldn't see it. And this was the lower edge of the screen, and all this, you could see that. But then you saw all this back here, all the stuff past this, and it was a rotten job. So have to do it over again. So what we're going to do is we're going to give you a few seconds to write all of this stuff down. Okay? These are the formulas that will allow you to figure out how much a certain billet will weigh given these dimensions. And you know, the dimensions are going to be what you need it to be. Okay? If you need it, you know, you're the one who's going to know what you need to have made. If you just want to make a standard sized billet and you've got a big pile of bronze laying there, and you know that, you know, bronze is one of your materials that, you know, it's a multi-use material. You can use it for anything from a pressure vessel, not a lot of pressure, but a pressure vessel, to a dog on a door for a ship, to a hammer. You know, it's a good general purpose material, like cast iron was, when cast iron was finally able to be used economically. So, you know, if you've got a big pile of scrap and it's just taking up a corner, and you want to, you know, melt it down and put it into a billet shape, here's your formulas. Now, there's two different types of billets with regards to the Navy's idea, you know, us doing it in the foundry. You have a solid billet, which basically, if I can keep from banging into the camera here, it basically a cylinder shape, just solid, just like that. Okay? If you're making a cored billet, that means you're going to be adding a core to the inside of this form to make a hole that goes through it, almost like making a pipe, except it's likely to be quite a thick wall. So a cored billet, if you had a drawing, would be kind of like that instead of solid. All right? Solid billet, shoot, you can make almost anything out of it that you know how to make, whether it be a piece for an engine, or a shaft, or small shaft, or a small rod, or a large rod, or anything. And these here with the big hole in them, they're more likely to be some kind of a spacer or washer, or, you know, it might even be something that was going to be this long, and that you had to have something to fit in here, or have this be a sleeve over something, whatever the case may be. But then this would be a cored billet. Okay? Now, there's two formulas that we were taught. We rarely went by because, well, our conditions in the foundry, it didn't require us to use them that often. But the conditions you will have, these might come in real handy. Now, don't forget, this video isn't for, you know, it's not designed and being recorded for the big foundries and you know, the ones who make billets all the time, because those guys are already going to have their own way of doing it, their own way of their own formulas, their own machines, their own techniques that they're going to do. This is for the hobbyist, the guy or gal who you know, has learned how to pour stuff, and also just might have their own machines that they can machine it by. Specifically, let's say there's two guys that I watch religiously, and one of them is Keith Rucker, and the other one is John over in England. And I'll be dadgummit if I can remember his name. It is his Turbo Boost, I think it was, or something like that. Anyways, I watch him all the time. Him and his also he likes to cook too. Okay, and I like to watch a lot of his stuff. I mean, there's the guys that oh, it's not Turbo Boost, it's Double Boost. Okay, I like to watch him. I like to watch him pouring metal too, and I like to watch, you know, both of them actually pour metal. I don't know if the other guys I watch all the time pour metal. I don't think I've ever seen A-bomb work like that, or not sure if Keith has got it set up. I've seen him, Keith Fanner that is, I've seen him pour Babbitt bearings, and but most of the other guys, they just have the machines, that lathes and such to work on. Anyway, those at least Double Boost and Keith Rucker, they do both cast, and they also have the machines of lathes and such to work in. They just to mention two, if amongst tens, got to be thousands of people out there that not only started off as machinery repairmen, but also decided to make themselves a little furnace and set themselves up a small foundry. They are going to be able to take advantage of this a lot more. Making materials, or actually just melting down and casting materials that has taken up room, that all the scrap, and they can make themselves some billets that they can make other things with. Okay, so back to the formulas. We use it once in a while. You're probably going to use it a lot more, and I've got everything here that you need to figure out the weight of a solid billet. Now, they gave us these formulas with the probability that what we're going to get is we're going to get a drawing that tells us the diameters, the heights, what metal they need to have it made out of, whatever drawing or specifications that would be on that drawing. We would have that, and then we would plug this in together, and then we'd find out how much metal we needed to, plus 25%, needed to melt down and make that particular billet. Okay? But you might be doing it the other way. If you have let's say a crucible that only holds 50 pounds, well, and let's say that's even at the 75% mark, because you can't have your crucible totally full. Totally on. It's absolutely the most dangerous thing you can do. And one of the safety rules that we had in the foundry is that maximum that we had inside the crucible was 80%. Okay, so let's say at 80% of your crucible comes up with 50 pounds, then the max you can have is 50 pounds. So your weight of solid billet is 50 pounds, or your weight of cord billet is 50 pounds. Okay, then you got to work the other way. You got to figure out. You've already got pi, which is 3.14. You're gonna know the material, okay, whether it be brass or bronze, but then you're gonna have to figure out whether or not you want it a certain height, or whether or not you want it a certain diameter. You're gonna have to make that decision. Once you make that decision, then you can do the math, and you'll find out for a given diameter, it'll wind up being that tall. Or for a given height, it'll wind up being this diameter. Okay? That will be one of those things that you're going to have to define, knowing how much actual maximum metal you can safely pour to consolidate all that scrap. Okay? So, this is one formula, this is a different formula. The weight of a solid billet, a solid cylinder, you get pi 3.1416, or if you want to make it even simpler yet, just 3.14 times big R square, which would be the radius of, and now this is just a solid one, so ignore these hidden lines. You just a radius of the half of the diameter of your billet squared times the height times the weight of the metal. Okay, simple, easy formula to do, even for me. And I'm not a math whiz at all. Okay, now let's pretend that you have to make a series of washers or a series of some kind of you know rings. Maybe you might have to make. So you need a cord billet. All right, and it's not one of those where you would want to spend all the time to bore out the inside of a solid piece of metal. When you make these billets, when you cast them yourself, yeah, you're going to have to take a certain amount off on the outside and a certain amount off on the skin, take the skin off on the inside. And the machinist repairman down in the machine shop told me that was anywhere between a 1/4 inch to 1/8 of an inch, depending on how rough the surface was. Yeah, you can take that off, but then after that, you can use a boring bar and put it out to the diameter that you needed on the inside. But there's that. How much is that saving you? When it comes to, instead of using a huge drill bit and boring it out and all that, you have most of it already gone, not even been there, and all you need to do is using a boring bar and finish it to size. So, and that's a cord billet. The weight of a cord billet can be found out by multiplying pi times the large diameter square, or large radius squared, that's this, minus little radius squared, which would be there between these 2 points, the middle of this and the edge of the core. Okay, big R square minus little r square times the height times the weight of the metal. Okay, and if you're going to be casting your own billets, those are the most useful formulas that I know. Now, you'll know this number. You'll know how much weight you got. You make a decision on which one you want, whether it be the diameter, a certain diameter, or a certain height. Now, the weight of the metals, that weight, that figure that you plug into the formula is the pounds per cubic inch that a certain metal weighs. And that's what you have here, pounds per cubic inch. For steel weighs about 1/4 of a pound per cubic inch, 0.28. Monel weighs 0.32 pounds per cubic inch. The lightest metal that you're likely to put your hands on only weighs about 9/100ths of a pound per cubic inch. Copper weighs 0.32 pounds per cubic inch. Iron, 0.27 pounds per cubic inch. Lead, the heaviest metal that you're likely to be working with, 0.41 pounds per cubic inch. Zinc, 0.26. Brass, 0.31. And bronze, because it has more copper in it than brass does, it makes it just slightly heavier, 0.32 pounds per cubic inch. Okay, go ahead and pause the video. I'm going to do a 5 count inside my head, and then actually I'm going to turn this off, get this stuff out of the way, and put some more stuff on here. Hopefully I be able to see that this will work instead of screwing up like I did last time. Be back in a bit. Okay then, now we're going to show you how to ram up and make your own billets. Okay, you figured out how much money, how much metal you need to have. You got your furnace all set up. You're ready to start melting down the metal. Okay, now all you need to do now is to make up. And let's pretend you already have the size or the pattern. Okay, or somebody made it for you. Whatever the case may be, you have a pattern, the size and height that you want for the amount of metal that you can pour. Okay. Now, if you've been ramming up, this is going to be just a bit different. I don't know if anybody ever has learned what a cheek is. C-H-E-E-K, cheek. But this is probably going to be a new thing. In your flask, you normally have a cope, and a drag, right? Well, in this case, this is going to be your drag, and this is going to be the cheek. Now, anytime you use a cheek, you can have one cheek, you can have a dozen cheeks. Okay, depending on how tall that represents off the ground, how pardon me, or how much metal that represents coming out of the furnace in your crucible. As I probably said before, and I'm sure I have, we usually used what's called a number 70 clay graphite crucible, which safely held 250 pounds, if I remember rightly. I think it is. And yeah, and so we knew when we were making billets that all we had to do is just ram up the pattern, give ourselves 80% in our crucible, pour the billet, and if there's anything left over, pour it into an ingot mold, which we usually had 2 or 3 cast iron ingot molds that had a wall thickness about an inch thick. Pretty heavy duty, but they also were going to last forever. Okay, so in the Navy, we had that capability. We didn't need that math, but you're likely to need that math, so make sure you write that down in a notebook so you can use it. In this case, most of the time, all we had when we were making billets is we had to have a 3-piece flask. Okay, drag, cheek, coat. Now on these pieces here, you had to make sure that for the alignment for the pins, that the bottom of that portion had to have something to receive the pin. Same here. If that one's a pin, this one had to have a piece of metal to receive it. Same thing on this side, okay? So that when you ram this up, you put the cheek on there, you put the pattern for the billet in there, you ram up this section, you put this on there, you ram up this section, and when it comes time to take this apart, these pins will line up, those 3, the same way you took them apart. As long as you can't get it mixed up, okay? So you've got thank goodness for whiteboards instead of blackboards and chalk. You've got the bottom part. Now this is going to be all sand. You need to have a base or a foundation for that billet. The billet, once you ram that up, gets put into the best place that you can think of, so that you give yourself not only sand in between the molten metal and the outside of the pattern, or rather the outside of the flask, which, let's pretend that we have a cutaway drawing here. Okay, so that's all rammed up. You ram this part up, then you ram this part up. Before you take this off, now you're going to have to put a sprue in there, but there's two different ways to make a sprue. Okay, you can take your sprue cutter and you take it, and you've already planned ahead where you want to have your runners and your ingates right? So you know where your sprue cutter is going to be pushed. Let's say it's right here. You cut it down, you push it down just a smidgen past this parting line. Okay? Then you cut your pouring basin, which is going to be kind of like that. Then this portion is almost ready. But before you take that apart, you've got this to take out. You've got this completed. But what you need to do before you take this all apart, because it's easier to do it right now than before you take it apart. Let's say I'm looking downwardly at it from above. Okay. I've made my pouring basin. There's my hole. And here's the hole representing the mold cavity for the billet. You need to take a piece of rod that's long enough to at least go to this parting line and do vent holes all the way around. Make certain that you do that before you do anything else, but you also go everywhere, because when you're pouring this, you want to make certain all the gases get out. Okay, once you cut your sprue and your pouring basin and you do your vents, then you put a draw pin in the top. Okay, and you tap it, or you wrap it, what we call wrapping it, all the way around, just so you can make yourself a little bit of a clearance all around this pattern. Now this is already going to have some draft on it, okay, up to, but not past, normally 5 degrees of draft. It can be 1.5 degrees. It can be, almost, it can be half a degree, depending on your foundry, the way that you want to do it. If you want to make it easier on yourself, you're going to be putting 5 degrees on there just so as you can pull it out without much fight. All right, but keeping in mind though, wherever this draft is, this down here is going to represent what what the metal is that they're going to have at the end, because they're going to have extra up here. So they're going, when they put it into the lathe, they're going to start down here and they're going to go up there and they're going to take off a little bit more and a little bit more and a little bit more until this end is the same as that end. Okay, so this is going to be bigger than down here so that you can pull it out easy. So this is done. You've got that done. You've pulled this out. Now you've taken this and you've pulled it up and you've taken it, sat it someplace. Somebody is going to take some parting powder, take a nice soft brush, and this sharp edge right here, where these two parting lines meet, they're going to break those edges so none of that can be turned into loose sand when you're pouring the metal, and will get into the mold cavity. One thing I do know, machinists hate sand in their metal. It'll mess up their tools big time and deaden, the edge that they took so much time to put into it. That'll deaden that. Okay, dull it out. So make certain, if you're making something that's going to be machined, no sand whatsoever. Now, okay, you've taken that. Now all you have is this. All right, you will have already done the vents. All right, so you don't have to vent the bottom like you did the top, or rather the cheek like you did the top. Okay, well, what you do have to do is you do have to, on this side, you do have to put the runners and the end gates. Okay. Now down here, what you're going to do is, see, when you take this off, this is going to have a little divot in here where you cut past this line. It's going to show where you need to go further down. This is going to be tapered. You're going to push past this point here. That's going to be tapered too. Now it's not going to be any more tapered than this was compared to that, but at least this will slow down, not slow down, but will, you know, control the flow enough that it isn't a free fall down here. As a matter of fact, if you pour here, it's basically going to rebound and not make as nearly as much dross that you would have if you poured it straight down. Okay, so you're taking this off, you're putting it, now you cut your down sprue, and now you're down to here. Okay, essentially all you got to do now is you take this somewhere and you take care of all the sharp edges, whether it be at the top of this sprue and the bottom of the sprue and these edges right here. You want to take all that sharp edges off with a light brush and make sure that there isn't anything that can be knocked off by the agitation of the metal and deposited into your mold cavity. Okay, now what you have down here is you have the bottom of your gating system. Now let's look at that. Well, I'll do it down here. I'll leave that alone. You're looking at it from the top again. We don't need this. Okay. This is the drag. Now, when you make this, when you ram this up, you're not gonna, you're not gonna be able to keep this from moving always. So when you look down here on this, the bottommost portion, you're going to have an outline, some kind of outline of where your billet's going to be. Okay, so if you want to make your job a little bit easier, you can take that billet, sit it in that outline, take something like a scribe and go around the outside so you can get the curvatures of the wall just right. Because what you're going to do is you're not only going to make a splash basin and a runner long enough for dross to make it, to the end here, get pushed into the end here and captured, but you're also going to be making an end gate here, but it's going to be an end gate you're not likely to have made before. This is called a whirl end gate. Now, you know what a whirlpool is, whereas if you looked at it sideways, it's kind of like a tornado in the water, going round and round and round and round. Okay, the whirl gate kind of simulates that. And there's a really distinct reason why you got to do this. Now, it's a little bit extra work than you're used to, because usually all they wound up doing in the past is just hitting it straight in like that, and then once this fills up to a certain degree, like maybe right about here, the gating system you're going to cut up here starts to back up and starts to pour in there. Okay, what you're doing this time though is your whirl gate is going to aim the metal so that it hits this wall, and the curvature of that wall is going to force the metal to follow the wall as this fills up. Okay, it's all going to move, all bite sluggishly, but it'll all move round and round like a counterclockwise motion. And I'll explain why that is in a second. So drag, splash basin, runner. And I've seen both this kind and I've seen this kind. Okay. And the runner is underneath it. Now the reason why this is kind of strange looking is because this is going to be in your drag along with this and this, but this could also be in your cope. This is represented by this. This portion, you know, as long as you can remember where your runner is going to be and you make sure that you intersect that area, you can have it up in here like that. That'll ensure that despite any turbulence you might see in here, despite anything that goes on in here, this is going to absolutely fill first. This is absolutely going to fill second. And if this will not have a bit of metal going into it until this runner is pressurized and backs up, and then this gets filled in there. It follows the wall, turns round and round. Okay? Now, here's the reason why we want that to happen. In the old way of doing things, without the whirl gate, just a regular old end gate, looking at it from the side, be like this, be like that's the runner, and the splash basin's out this way somewhere. This fills up, it overflows the edge, goes into here, straight into here, and whatever didn't get pushed all the way to the end of this runner gets pushed into here. And when it gets pushed here and it starts filling up, usually the stuff gets deposited here, might get deposited on that wall, might be here. As it goes up a little bit, something might come up here and deposit up in there. Okay, from the hydrostatic pressure, whatever sand you didn't blow out, whatever dross didn't get pushed to the end of the runner, whatever bad stuff that's going to happen is going to happen by using the straight in approach. If you make it, or if you, I highly suggest that you do it. If you make a whirl gate and you force the metal to conform, you know, follow the outside skin of the billet in the mold cavity, the stuff that has a tendency to attach itself to the walls, and even the stuff that might attach itself into crevices, you're going to have that metal pushing against it, dislodging it. And because these particles and these bits of junk is not pure metal, it might be partial pure metal and partial metal and oxygen. That stuff, the defects, even the sand, is lighter in density than this metal. And so that stuff, as long as it isn't allowed to rest against the side of the mold cavity, will float in the mixture. And eventually, once this fills all the way up, all the bad stuff will have surfaced when you stopped pouring this. Okay? So that's why the whirl gate. Okay? And as I showed, you can have the whirl gate, you can form the whirl gate first in the, let's say you're doing it in the drag, and then form the runner second and then the splash basin, or you can form the whirl gate on the top section and then the bottom half on the drag, runner and splash basin. Same can be set up here. Okay, once this starts filling up, it'll get to the point where the force that you're exerting here is no longer sufficient to keep this going up, because you'll have more weight over here than you have pouring here, and so this will slow down, and this will solidify or slow down enough to where it starts getting plugged up, and the gating system that you make up here at this split, at this parting line, will then take over, filling this the rest of the way up. Okay, do it the same way as you did down here. You just don't have to make a splash basin. Okay, let's say this is the parting line for here. Okay, you have a hole made, you have the mold cavity. All you got to do is cut yourself a runner, and then whether you put it on the same face as the runner or whether you put it on the face up here, okay, you make sure that your whirl gate conforms with that force, or rather that curvature of the wall here, so that that metal can continue to move and prevent any bad stuff from lodging on the walls. Okay, much easier for the machinists to, you know, part off the end of this and you know, make this square, and if they know that there's crap up there, they can make allowances for it. Then it's much easier for that to take place than for them to go along here trying to turn this down and them hitting a chunk of metal that's you know, that dross, it's a bunch of junk, or if it's a piece of lodged sand, very bad. Okay, let's see, let's try and catch up with my brain here. You've got this made, you've got the metal, yeah, you've got, oh, okay, here you go. I knew there was just a little something that I was not saying yet. Okay, this stuff is filling up, right? Filling up. It comes out, start coming out of here. You've got this head height here that's forcing the metal to come in here. Okay. But you don't necessarily want all the hot metal right here, right? The cold metal, hot metal, it's just like a riser. You want it to freeze up down here, and the directional solidification progress in that direction. Okay, so once it starts getting about to, let's say, halfway between this parting line and the top, stop pouring there, come over here and fill it the rest of the way here. You will ensure that your coldest metal is here, your hottest metal is here, and that whatever was in here will get pushed up here, because you're going to be pouring it in there and it'll be almost turbulence right in here, but you're not going to be so far away that you're making new dross. Okay, but once you fill that up, you'll have the advantage of knowing that this is all hot metal, this is cool metal. By the time you do that, this is already frozen, this is getting ready to freeze, and once you get done with it, you'll be able to cut this off at the bottom, you'll be able to cut that off there, and you'll be able to take that and put it in the lathe and turn it down into some nice clean metal, something you can use, and you've saved yourself a few $100s. Okay, so I hope I wasn't too bad with the math. If anybody has any questions about this, if any of you molders, if I dropped a stitch here, if I forgot a step, you know, it has been 30 some odd years, please put them in the comments and then I'll address it. And I very much hope that you guys who not only melt metal but also use lathes and milling machines are able to take advantage of this information, and all that stuff you've been having in the corner piling up and piling up. You can now make yourself something that someday you're going to use it. You're going to take advantage of it and you're going to use it. Okay, so this is the end. I don't yet know what my next subject matter is, but this I've been really wanting to show everybody because it ties together both the machinery and the foundry. And we'll see you later. And those of you who know what this means, Liberty Call.